great. So we are totally switching gears now. And the next about 4 weeks actually is dedicated to a new topic. Officially, the topic is called linear algebra, and it involves something called matrices. And one of the applications of these matrices is it gives us a way of solving systems of equations that are more complicated. So, but we're going to start with just your basic 2x2 system of equations. And would you take a minute to use whatever method you like to find the value of x and y that satisfy this system of equations? So go ahead and do that. And you can type your answers into the chat as you get them. Okay, so I put up the two different solutions here. Whether you currently have two methods for solving systems of equations. You have the substitution method, where you can solve for y in terms of x and then substitute in for the y in the other equation. And you do get 5 and 3, which a lot of people wrote on the chat. More popular way of doing this is to do what's called the elimination method, where you somehow multiply one of the equations by some number that will make it so that when you add or subtract the two equations, one of the variables drops out. In this case, the y's do, and you're left with an equation with only one variable, which you can solve. And once you have that variable solved for, you can plug in to either of the two equations to get the value of y. So those are our typical two methods of doing this. And I want to say a little bit about the elimination method. First, I should mention that on Monday, you can bring your graph, if you brought your graphing calculator home with you on March 13th, then you could have it. It's not totally necessary to have, but if you have it with you on Monday. I want to say a little bit about this elimination method, because we learned it back maybe in 9th grade, even 8th grade, but it's really kind of mysterious, like why does it work? And I want to tell you a little bit about that. So we know that the answer is 5, 3. And 5, 3 does make both of these equations true. Now, what happens when you add two equations together? Just add, not trying to eliminate, but you literally just add the two equations together. Is there any significance to this new equation? Like, let's say I didn't know the answer, but I just added them. Didn't eliminate, just literally added these two equations together. Any insights about this equation that's formed by adding two equations together? Because each of these equations individually has an infinite number of answers. Like 5,3 does happen to make both of them true, but 0,13, for instance, makes this true, top one, but not the bottom one. Yeah, we could put any of these equations into slope-intercept form, and maybe if it's got a negative y, it's easier to, but what can you say about this equation? Any insights? Okay, so I saw about the average. If so, there was mention about graphing. 2x plus y equals 13. And 3x minus 2y. Let's see, that would have 0 negative. So here's a graph of the two lines. I just want to sort of follow through this idea of, is there some significance to the graph? So here, this top equation is this line. And this bottom equation is that line. Is there something going on with this, this new equation? Like if I were to graph that? And yes, I see somebody said, this is Keller. Who's that? It says if you plug 5,3, last name. If you plug in 5,3, so it also works. So all we can really say about this equation is that it's also going to pass through this intersection point. You see, a lot of numbers make this first equation true, including 5,3. A lot of pairs of numbers make the second equation true, including 5,3. And a lot of pairs of numbers make this third equation true. But one of them is definitely going to be 5,3. Because if it's true that, let's say I just took, let's just say now I know that 5,3 is the answer. Well, that means that 2 times 5 plus 3 equals 13. And it's also true that 3 times 5 minus 2 times 3 equals 9. So if I add those two equations together, and I think of the 5s almost like terms, I get 5 times 5 minus 1 times 3 equals 22. So all three of these equations have this point in them. The thing that makes both equations true originally will also make this new equation true. We really don't know much else about it because this 5x minus y equals 22 has an infinite number of points on it. But all we really know, if I put 0 in for x, I would end up with, something like a point down there. And if I put 0 in for y, something like that. So what I'm getting at is when you add two equations together, the brand new equation will go through. If the original two equations have a common point, this third equation will also have that point in its solution set. But it really doesn't help us get the answer in this case because this thing has so many points on it, so adding them together doesn't really help us much. But if I were to take these two things And instead, let me bring up a new page. Two x plus y equals 13. And the other one was 3x minus 2y equals 9. Well, when you multiply this top equation by 2, what happens to the graph? What happens to the graph of an equation if I multiply the left and right side by 2? What happens to the graph of the solution set? You can type it in. How does the graph of 4x minus 2y equals 26 compare to the graph of 2x plus y equals 13? Oh, and somebody's trying to get in. Okay, they're in now. Okay, so Talia mentioned about when you multiply the slope and the y, so some kind of like almost a dilation. It's actually not going to be, it's not quite that. How about this question? How does the solution set change? Like there's a bunch of ordered pairs that make this equation true. And if I double everything, what happens to the solution set? Well, you know, you could, if you turn this original one into slope-intercept form, you get that. What would happen if you turned this new equation, the 4x minus 2y equals 26, into slope-intercept form? And Youssef is right. Nothing happens. The graph stays exactly the same. So whatever point it was that whatever the intersection points of these two lines are, it doesn't change by multiplying an equation by 2. When I multiply both sides of the equation by 2, the solution set stays exactly the same. So all three of these lines pass through whatever the intersection point is. Let's say we don't know what it is, but this new line up here will pass through it also because it's the same as this one that was in the middle. But now when I add them together, I get 7x equals 35, which is the horizontal line, sorry, the vertical line, x equals 5. So now I have the two lines and the third line like that. And they all pass through the, oh, it was plus 2y. Wait. It was y equals 2x minus 13, sorry. Wait, it was 2x plus y, so y equals negative 2x plus 13. Okay, but as I was saying, now when you add them together, you get this vertical line. And all we can say about this vertical line is that the intersection point is on that vertical line. But every point on that vertical line has x equal 5. So that means that the intersection point must be 5 comma something. That's what's going on. That is very sophisticated why the elimination method works. But that's why it works. It works because when you combine two equations, the new equation will contain the intersection points. And if every point in the new equation has x equal 5, that means the intersection point has to have x equals 5 also. Okay, so that's like a new thing that you probably didn't give much thought to when you learned systems of equations. Okay, now today's lesson is about a new method of solving systems. Now, you could write down this 3x3 system. We're not going to do this right now, this system itself, because if you remember from last year, 3x3 systems of equations are really complicated and kind of annoying. You have to pick a variable to eliminate from two of the equations and then pick a different pair and make the same equation and same variable eliminate. Then you have to take those two equations and make one of those two variables eliminate. And then you get one answer, and then you plug it into one of those two new equations to get the second answer. And you plug those two answers into one of the original equations to get the third answer. And it's a lengthy process. And you could imagine if it's a 4x4 system, that's going to be even worse. Today's method is going to be to somehow convert a 3x3 system of equations into a 3x3 system again that looks more like this. An equation like this, where the top equation, in a system like this, where the top equation has all three variables, the middle equation has just two variables, and the third equation has just one variable. When that happens, it's called upper triangular form because this looks like a right triangle. And when it's in this form, it's real easy because you can take the last equation, divide both sides by 5 to get 4. Then you could go up the ladder, take the middle equation and the z value that you just figured out. And then you can take the z and the y that you figured out and plug them into the top equation. So it's really good if it's really good if the original equation is already in upper triangular form. There's no real work to do anymore. But sometimes I will get a question like that, but what if it's not? And for this, I'm going to teach you a new technique that's called Gaussian elimination. And I think I'm going to show it to you with that, I'm going to show it to you in 2x2 first. So 2, 1, 13, 3, 2, negative 9. So sorry about that, negative 2, 9. And we know the answer is 5, 3, just on the side. Okay, so here is how Gaussian elimination works. With a 2x2 system, it's a two-step process. Step 1 is to get this 2, change it to a 1 somehow. And the way we do that is by multiplying the entire top equation by 1/2. And we copy the second equation. Just so you know, for a 2x2 equation, this is not the way you would actually want it. This is, I'm just going to teach you the method because it's going to be good for 3x3s and things like that, but it actually takes longer to do a 2x2 this way, but it will at least show you sort of what the method is. And step 2, we are going to multiply the top equation. Oh, well, the goal of step 2 is to make that into a 0. And one of the things we're allowed to do is, like we did in step one, we're allowed to multiply both sides of the equation by something, but I don't want to multiply both sides by 0 because that would get rid of the entire equation. So another thing you're allowed to do, oh, and someone needs to be admitted. There's 3 things you're allowed to do. One of them is you're allowed to multiply both sides by a constant, which is what we did in step 1 to change the 2 into 1. But another thing you're allowed to do, and listen carefully, you are allowed to take any of the equations, multiply them by whatever constant you want, and then add to the other equation. But only the other equation is actually going to change. So take a look. I'm going to copy down the first line that I have so far. That doesn't change. Only one equation changes at a time. But the way I change this third equation is, in my mind, I think, okay, if I did multiply this top equation by -3, namely the opposite of this number, and then I added the new number, which is -3x, to the bottom one, it would become 0x. I'm going to write 0x now, although just to show you that it would have been there. So what I did is I multiplied this row by -3, and then I added it to the equation. I'll write equation 2. I wrote equation 1 times -3 plus equation 2. And that answer got replaced, equation 2 got replaced with it. But equation 1 did not actually change. Equation 1 did get multiplied by -3 and then added to equation 2, but equation 1 itself doesn't actually change over here. It just kind of changes in your mind for a second. -3 times 1x is -3x plus 3x is 0. -3 times a half y is -3 over 2y plus -2. So it's -3 over 2 minus 2, which is -4 over 2, is -7 over 2y. And finally, multiply this by -3, you get -39 over 2. And you add it to the 9, which is the same thing as 18 over 2. So it becomes -21 over 2. Now you might say, well, this seems like extremely hard way to do this question. And you'd be right. This is not the way we'd ever really solve a 2x2 equation. But this idea is going to be very powerful for more advanced equations that are coming up over the next bunch of lessons. Let me continue with this now. Notice how x plus 1/2 y equals 3 over 2 and -7 over 2y equals -21 over 2. That is in upper triangular form. Upper triangular form is where basically for a 2x2, its width is a 0 in the bottom left-hand corner. We made this a 1 first because that 1 made it easier to change this into a 0, because once this was a 1x, it was real obvious that it's -3 I need to multiply by to eliminate the +3. If I left this as a 2, not that it's illegal to do that, but then you'd have to it would be more confusing what thing to multiply by. Anyway, this thing's upper triangular, so now I can say -7 over 2, y equals -21 over 2, y equals -21 over 2 times -2 over 7, and it became 3. And then I plug that 3 into the top equation, x plus 3 over 2 Anyone know what went wrong there? Is that a 3 over 2? Oh, it's a 13 over 2. Equals 13 over 2. Subtract 3 over 2 from both sides. X equals 10 over 2 equals 5. And that's what the answer is. 3 and 5, 5 comma 3. Okay, so you're looking at that and saying, I don't like this method because I had two methods that I could do so easily before. Well, we're never going to do elimination, Gaussian. This is called Gaussian elimination. When you try to get the system into this upper triangular form, we would never do that for a 2x2 system of equations, except this one time. Now, Ethan, you said here if you multiply by 1/2, do you mean back over here when I changed this into a 1 by multiplying by 1/2? Yeah, so the second equation, that could be anything, because once we've turned this 2 into a 1, we can get rid of it. We can make this guy eliminate by multiplying by whatever the opposite of that number is. I think I'm going to show you for a 3x3 equation now. And that's all we have today. We have this system. Now, this is a pretty cumbersome method for 3x3 also. It actually takes 1, 2, 3, 4. It takes 5 steps. And I'm going to go through what those steps are. Whoops. 5 steps. Those steps are going to be to turn, eventually it's going to be like this. Those are the 5 steps. So step 1 is to somehow get that, it already is a 1x, so that's good. Step 2 is to turn that to a 0. Step 3 is to turn that to a 0. Step 4 is to change that to a 1. And step 5 is to change that to a 0. If I do that, this thing will be in upper triangular form. I should mention there is a third thing you're allowed to do. So one thing you're allowed to do is to multiply both sides of an equation by a number. The third thing you're allowed to do, even though I told it to you second, is you can multiply something by a number, one equation by a number, add it to the other equation, and replace the other equation with that sum. And another thing you're allowed to do is you're allowed to swap the position of any two equations. There's no reason to here, but let's say this was already a 0 up here. Let's say that was already a 0. Then the only way to get it to be a 1 would be to swap. Okay, here we go. We'll go through the 5 steps. This is it for today. This is the instructive question of the day. Step 1's already done because that x is already a 1x. But if it wasn't, if it was a 3, I would have to multiply the whole equation by 1/3. Step 2, I'm going to take -2 times equation 1, add it to equation 2, and replace equation 2 with that new answer. So only one row changes each time you do one of these sort of operations. I'm leaving some room here in the middle. See, I did -2 because that will cause this to become a 0. I come up here, I go -2 times x is -2x plus 2x is 0x. Don't need to write it, I'm just writing it for instructional purposes. -2 times 2y is -4y plus y is -3y. -2 times z is -2z plus z is -z. And -2 times 3 is -6 plus 16 is +10. So now I've accomplished step 2. Can someone type into the comments, what's step 3 going to be? If I were to write out it in like a shorthand like this, what would be step 3? What would I do to make that into a 0x to get rid of that x there. Does someone want to unmute themselves and say it? Because now we have Zoom. It's better you just push spacebar and start talking.
Do you use the first equation to cancel out the x term in the third?
Can you say it in like this form? Like here I said negative 2 E1 plus E2 goes into E2.
So E1 plus E3 goes into E3, but usually you would have to, like the original equation for E1, because you don't have to multiply it by a constant in this case.
But I think you need negative E1 because,
yeah.
And I should mention, you might think, oh, well, also could I just subtract instead? And though you are technically allowed to, we will always put a plus sign here. So it's negative E1 plus E3 goes into E3. So this means I take this system here, I leave row 1 alone, even though row 1 or equation 1 is going to get multiplied by negative 1, it's not actually going to change. It just gets done in our mind. So we go to here, negative x plus x is 0x, step 3 is working. Negative 2y plus y is negative y. Negative z plus 2z is plus z. And don't forget about this, negative 3 plus 9 is 6. Okay, so now step 4 is to get this thing to be a 1. And what's the most, what's one way you might do that? You can unmute and say what's one way of doing it, and then there's going to be a second way that takes 2 steps, but might be even faster with the 2 steps. But someone give me what's the 1-step way you could unmute yourself and say. That's right. Divide E2 by 3. It should be negative 3 though. So you could do, and I'll write it this way, negative 1/3 E2 turns into E2. And that would be fine. But the reason we need the negative is because we want to turn this into a positive 1. But that's going to lead to fractions. And sometimes we can't avoid the fractions. But there's actually a second way to do it. It would take 2 steps. And I'll tell you that you are allowed to swap any 2 rows. So you could also accomplish this by swapping equation 2 with equation 3. And notice how that would be okay because these things would still be zeros. Let me just go to another page for a second. Hold on. So I'm going to do this one. I'm actually going to do 2 steps because I do like to avoid the fractions as much as, oops, getting ahead of myself there. Tomorrow's lesson. X plus 2y plus z equals 3. Negative y plus z equals 6. Negative 3y minus 3z equals 10. That was E2 swap with E3. And now I can easily make that into a 1 by doing negative E2 becomes E2. So that was a 2-step method, but it was easier than, it avoided fractions. It's okay to have fractions. Some people don't mind the fractions. Well, I've accomplished step 1, step 2, step 3, and step 4. Someone want to unmute and tell me how I'm going to accomplish the final step? Step 5, you could say it as like an expression like this. Oh, did I? I see. I threw an extra 3 by accident. It's minus 3y minus regular z. Sorry about that. Okay, how am I going to make this y, this minus 3y, disappear? Anyone want to unmute and say it?
Multiply e2 by 3.
That's right. So the final step is 3e2 plus e3 goes to e3. So the first row doesn't change. The second row doesn't change. But the third row does change. Notice that this was already 0, so that because there's a 0 here, that's still going to be 0. But this is now going to cancel out the y because 3y minus 3y is 0y. But then when I multiply the z by negative 3 z minus 3 is negative 4z. And 3 times negative 6 is negative 18. Negative 18 plus 10 is negative 8. Incidentally, we very rarely do this process either, because this is going to give it, we're going to get a shorthand for this tomorrow, but this is like the idea of what's going on. Notice how it has now been made upper triangular. So z equals 2, because I divided both sides by negative 4. And if z is 2, y minus 2 equals negative 6. So y equals negative 4. And then if I plug that 2 and negative 4 into this top equation, I would get x minus 8 plus 2 equals 3. X minus 6 equals 3. X equals 9. 9, negative 4, 2. Let me just make sure that's right. Oh, I see. With this version of Sketchpad, I'm not of Smart Notebook, I'm not able to see. Well, I do believe that that's the answer. Let me just do a quick look. Hold on a second. Okay, everybody. So yes, it is right. 9, negative 4, 2. And that's actually today's lesson. I mean, there's practice questions to do for homework. They get pretty complicated, but that's the basic idea, this 5-step process. In summary, these are the 3 what are called elementary operations. You are permitted to take a row, multiply it by some number. We could even go like this. And I should. So you can take any row, multiply it by a number that's not 0, and replace that row with the new thing. You can swap any 2 rows, or you could multiply some row by a number, add it to another row, and replace the row that got added to with the new sum. This rule is used for making ones. You know, when you want to have like 1x and 1y. This rule is for making zeros. When you want to have that and that and that. And this rule is just to avoid fractions, or to, if there's a 0 somewhere and you need to turn a 0 into a 1 or something, you can swap that row as needed. Okay, so that's today's lesson. This entire thing, in case you're wondering what we've learned today, is called Gaussian elimination. And it is one of the most tedious things we learn, because tomorrow, or Monday that is, I teach you how we can do the same steps as Gaussian elimination with 1/4 the amount of writing. So it's the concept of Gaussian elimination that's going to be important, not all this writing. But for today, it's our first day. Oh, somebody, I just admitted. This thing makes a waiting room. Okay, so let me stop the recording now.